Okay, well, moving on into chapter 22, we'll start a new chapter on electrostatics, and I'll just kind of warn you ahead of time, this is going to be a longer chapter than usual. So we're going to introduce a new concept, and we'll be talking about electrical forces and this concept of charge that we've actually kind of talked about a little bit in Physics 101. We'll be talking about positive charge and negative charge. Charge is going to be conserved quantity. It can't be created or destroyed. And we'll talk about how much forces can be experienced between charges with Coulomb's law. We'll talk about conductors, insulators, semiconductors, and superconductors. Then we'll go ahead and talk about how we transfer charge and how we can mess around with charge through charging and charge polarization. And we'll finish off by talking about this field that surrounds charges called an electrical field. We'll talk about electrical potential, or voltage if you will. And then we'll talk about energy storage. So what exactly am I talking about when we talk about electricity or electrostatics? Well, common places that we'll see things like electricity would be something like lightning, or if we strike a match, you see that spark on the edge? What we're really seeing is we're seeing the transfer of charge. And actually, electrical charges are going to be what hold atoms together, and I have a quick little revisit on the chapter on atoms here in a couple of slides. Essentially, we'll be talking about how things can have charge. Again, we're going to be talking about charges that are positive and things that are negative. There's going to be a force that surrounds them. Opposites are going to attract, like charges are going to repel. And it turns out that there's kind of like this aura that surrounds charged particles. Kind of like if you remember, if you had something like a magnet has a north and a south, and you can make it stick to things that are metal. There's probably some field that surrounds this magnet that can interact with that metal or with another magnet. The same thing is going to surround charges, and it's called an electrical field. Now, when we talk about charged particles, we have our good friend Benjamin Franklin to thank for thinking about a lot of these. He realized that there are two types of charged particles. There's going to be a positively charged particle and a negatively charged particle. And in nature, we tend to see positively charged particles, which are called protons, and negatively charged particles, which tend to be called electrons. And these are kind of the fundamental building blocks of matter. And the proton is going to have a positive charge, the electron is going to have a negative charge. When we talk about charge, a lot of times we're going to see Q, and the Q is going to be positive or negative, and it just kind of represents charge. Like charges are going to repel, and a like charge could either be a positive and a positive, or a negative and a negative. And opposite charges are going to attract, so a negative charge would attract a positive charge and vice versa. These are Newton's third law pairs, and so there's equal but opposite forces on each one of these guys, so force and force. Now, the next couple of slides are going to talk about atoms, and this is kind of a revisit of Chapter 11 from Physics 101, but essentially the fact that opposite charges are going to attract each other are essentially what hold atoms together. So there's a force that charged particles are going to have, and their charge will tell you whether it's an attractive or repulsive nature. If we think about an atom, we know that atoms are made up of protons in the center, and protons have a positive charge associated with them. This one has 2. That kind of dictates that it's helium. And this one actually has some neutrons in there as well. Neutrons actually don't have any electrical charge, but they do have some mass. And again, protons have positive charges. And electrons are not very massive, and they live in kind of these orbits that surround this positively charged nucleus, kind of like planets go around the sun. And what kind of happens here is here we have a negative charge, here we have a positive charge, and there's going to be a force of attraction kind of like this, and there'd be a force of attraction like that, just like the sun attracts the Earth, and these guys are going to, for all intents and purposes, rotate around. Now, you may be saying to yourself, wait a minute, here we have a positive charge and here we have a positive charges, and surely these guys must repel each other, and in that sense you are correct. However, it turns out that these neutrons, for right now, let's just say that these neutrons that are inside the nucleus, they act like glue that can hold those protons together. More on that in several more chapters. Let's just get some more stuff about atoms out of the way. And essentially, atoms are going to have a positively charged nucleus, that's the protons, and they're surrounded by negatively charged electrons. And these electrons are going to live in very discrete orbits, and I'm actually going to call these orbits shells. And it turns out that only a certain number of electrons can live inside of these shells. And once we go ahead and fill these shells up, then actually we have to bump out to a higher shell. So this is hydrogen. It's got 1 proton and 1 electron. It doesn't have any neutrons. If I were to tack another positively charged nucleus on, or another positively charged proton into the nucleus, then to balance out the charge, I have to put an extra negatively charged electron in there, because pretty much most electrons or most atoms are electrically neutral. They have the same number of positive charges as negative charges, and technically there are 2 neutrons in here to hold this together, but we're going to ignore them for just a little bit. Now, as I go on and I add more positively charged protons right here, so this one would have an atomic number of 3, 1, 2, 3, I need to add another electron to make this neutral, but it turns out that this innermost electron orbit, or shell, if you will, is full. So we're going to have another orbit somewhere out here that's just a little bit further away. And it turns out how close you are makes a distance, or how close you are makes a difference. And this electron is not going to be bound nearly as tightly to this positively charged nucleus as the ones inside of the inner orbit. Just a few more facts. Keep in mind that protons are going to be positively charged, neutrons are going to be negatively charged, and these guys, for all intents and purposes, roughly have about equal mass. Not quite, but good enough for Physics 102. And most of the mass of atoms are made up by these two guys. Electrons are not very massive at all. They're about 1,000 times less massive than protons or neutrons. But bear in mind that a proton is going to have positive charge and an electron is going to have negative charge, and these charges are actually going to be equal but opposite. Again, neutrons are going to have no net charge. Again, most atoms are electrically neutral, so they have the same number of protons as they do neutrons. What happens if we have an imbalance of electrons? Well, we're actually going to have something called an ion. You've actually seen this slide before in Physics 101. And we're going to have positive ions or negative ions. A positive ion is just going to be missing an extra electron, so it's going to have a net positive charge. There's more protons than electrons. We could have a negative ion, and that one's just going to have an excess electron, and so there's going to be a net negative charge to this ion. Now, also to reiterate the point, we can talk about the electrons inside of an atom. Bear in mind that these things are going to live in these very discrete orbits that are called shells. And in chemistry, they call them like the S shells and the P shells and stuff like that. I'm not going to hit you over the head with that, but I do want you to know that electrons live inside of these orbits. And we can have electrons in inner orbits or in outer orbits. And here I'm showing you the same atom that I did before. It has 3 positive charges. It's going to have some neutrons in there as well, acting like glue, holding these guys together. Technically, this is lithium, and lithium is going to be dictated by the number of protons. And if this is electrically neutral, so not an ion, it's going to have 3 electrons, one living here, one living here. These are innermost electrons, and then we would have an outermost electron right here, living in some orbit or shell that is slightly further away. Bear in mind that all of these guys are attracted towards the nucleus, but the inner ones are attracted far more than the outer ones because, well, you get more force when you're closer to an object. Before I move on to the next slide, one thing that is really, really, really important is going to be when we talk about the transfer of charge, it's actually the electrons that do the moving. And there's a couple of reasons for that, and one of them is going to be that the electrons are not very massive compared to the protons or the neutrons, and that makes them move more easily. And secondly, all the protons are tied up inside of this nucleus. The electrons are free, and when we want to transfer charge, it's much, much, much easier to knock this electron out than it is to try to knock a proton out of the nucleus. So it's the electrons that do the moving whenever we transfer charge around. Now let's just talk really quickly about transferring some charge around. If you've ever brushed your hair with a comb or with a brush, especially in the wintertime when it's dry, then perhaps it's going to spark, perhaps your comb might be attracted to your hair. What might happen in this particular case is you're transferring, as I said, electrons, and they're going from your hair to the comb, and your hair is going to be lacking some electrons, and so your hair is going to be positively charged. So an example of that might be, here's your hair. You've gone ahead and you've transferred some of these electrons to your comb, and so the net charge on your hair is going to be positively charged. We can also just rub various materials together. Classic examples are glass with silk. Then what's going to happen is electrons are going to do the transferring. Bear in mind that it is the electrons that do the transferring, not the protons. Now, as we move charge around, one thing to bear in mind is that charge is going to be a conserved quantity. It's not going to be something that we can create. It's not going to be something that we can destroy. We can slosh charge around, but we can't simply create them or destroy them. For example, if we were to take this rod right here and rub it with a cloth, then what might happen is we might transfer some electrons, and if we go ahead and count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then we've transferred 10 electrons over there. This guy right here is going to have a positive charge that would essentially be 10 positive charges. Now, whenever I talk about charge, charge does have a unit, and the unit for charge is going to be a coulomb with a capital C, or C-O-U-L-O-U-M-B. And something to kind of keep in mind is how much charge does something like an electron have? Well, one electron is going to have roughly 1.6 times 10 to the negative 19th coulombs. You may be saying to yourself, wow, that's not a whole lot of charge. And a coulomb is actually a very, very, very large unit of charge. You may say to yourself, well, if one electron has 1.6 times 10 to the negative 19th coulombs, then how many coulombs or how many electrons does it take to make up one coulomb? Well, that's just going to be the inverse of this. So the inverse of 1.6 times 10 to the negative 19th coulomb. And if we go ahead and type this into your calculator, it's going to be 6.25 times 10 to the 18th. And that's going to be electrons now per coulomb. That's a lot of electrons. So electrons don't have a whole lot of charge to them, and a coulomb is a very, very, very large unit. Very often we're going to be talking about units of charge that might be in, say, micro coulomb or 10 to the minus 6 coulomb. So micro, it might be one of those prefixes that we're going to now start to see. Now, the last thing I want to talk about for this particular section is going to be net charge, and what we can kind of say is the net charge of an object is going to be the sum of all of its charges. If, for example, we had this glass rod, and this glass rod had 3 positive charges and 1 negative charge, then we might say that this thing is going to have a net charge of 2 positive charges. This silk cloth, we can do the same thing. We're going to have 2 positive and 4 negative, might have 2 negative charges. Now, when we talk about the attraction or repulsion, it's actually going to be the net charge of an object, because very frequently there will be many charges living inside of an object. Since we have 2 positive and 2 negative, then there's going to be a net force of attraction between these guys. A neutral object is going to have equal number of positive and negative, not going to have an excess or deficiency of electrons.